Yeah, thank you for your patience and uh, thank you very much for coming and for this week of high energy seminar. And today we have two speakers. The first speaker is Dr. Nuria Torres Alba, and she is from Clemson University. So Dr. Torres Alba is a postdoctoral fellow at Clemson University in Clemson, South Carolina. She obtained her PhD in 2019 at the University of Barcelona in Spain, and has been working at Clemson University ever since. Her research focused on active galactic nuclei and their surrounding across the electromagnetic spectrum. In particular, she has worked on the interplay between the star formation and AGN activity in luminous infrared galaxies, determination of the compton-thick AGN fraction in the local universe, as well as the modeling of gamma ray emission produced in the interaction between AGN jets and obstacles. Her current research is focused on characterizing the AGN torus via X-ray observations. And so the floor is yours.
Thank you, Shuri. All right, so like Shuri said, I'm now working at Clemson University, and I actually work very closely with Shuri in trying to use X-ray observations to determine some properties of the torus or the obscuring material surrounding the AGN via X-ray spectroscopy. So I'm gonna briefly talk about the AGN structure, but I'm only gonna mention things that are necessary to understand the X-ray spectrum of an AGN. The first element that we need to produce the X-ray photons is an accretion disk, which generates a thermal emission in the infrared to UV range. Then we also know that we do not see this emission from all directions. We may have an obscuring torus in our line of sight, and then we talk about an obscured AGN, or we may also be looking at the torus to an unobscured direction, seeing an unobscured AGN. The X-rays in particular come from the corona of the AGN, and the corona is just a hot plasma of electrons. We don't know exactly where it is and how it's shaped, but we know that the photons from the accretion disk interact with these hot electrons to get upscattered to X-ray photons via inverse Compton scattering. And this will result in a spectrum such as what you're seeing there, where the line on the top that says unobscured, just in the shape of a power law with eventually a high energy cutoff. If we're seeing this AGN through an obscuring medium, so through the torus, we will be seeing an obscuration more intense at lower energies than at higher energies, that increases and increases its effect the more material that we have in our line of sight. We talk about the obscuring column density in particles per centimeter squared. So, however, we know that the obscuring material, it's not quite as simple as a perfect homogeneous torus. We know nowadays that this material is likely patchy. We know this from infrared studies that are probing the emission of the dust via SED modeling, but we also know this thanks to occultation events that have been observed in X-rays. So events in which the obscuration in the line of sight changes from one epoch to the other. And these changes can be happening in timescales as short as less than a day and as long as years. And this is how we would see the effects of a change of obscuration in the X-ray spectrum of an AGN. So our initial intrinsic power law is being obscured in two different manners at two different epochs. The blue epoch has higher obscuration. This is a simulated spectrum that is showing then in these confidence contours, which are just showing NH in the line of sight, or column density in the line of sight, versus photon index at the two different epochs. And we can see that we can disentangle in a spectrum that looks quite like this, the NH in the line of sight at the two different epochs as being different at the 3 sigma confidence level. So far I've talked about the X-ray emission of the AGN as a one single component, or what we would call the line of sight emission. This initial intrinsic power law coming from the corona gets obscured in our line of sight. So part of it gets diminished, not all of it gets to us. However, this is not the only component in the X-ray spectrum of an AGN. We also have a reflected or reprocessed component. So this happens when the intrinsic emission of the corona that is emitted in all directions collides with the particles in the torus and can get redirected to our direction and get into our line of sight through Compton scattering. And this affects the shape of the X-ray spectrum we would have a reflection hump, such as the one that I am showing here. This would be the result, an added component to the X-ray spectrum of an AGN after it has interacted with the whole of the torus. So something that's important to remember about this component is that it's representative of the whole of the reflecting material. So it's giving us information on the average properties of all the material that is contributing to the reflection. So in principle, of all of the torus, not only a line of sight property, right? And this is also the component that would result in this very prominent emission line, so particularly the iron emission line, which is very distinguishable in X-ray spectra of an AGN. So this component, this reflecting component that we're particularly interested in, is it can take various shapes depending on the shape of this reflecting material. And in here, I'm just showing some plots done by Shuri, actually, that showcase, using one of the various models of the reflector, how a change in covering factor. So for example, if this torus is very physically thin or thick, can change the shape of the emission. The inclination angle through which we are seeing this AGN can also change the shape, and also the average column density of the torus. So whether this torus is optically thick or optically thin can change strongly the shape of this reflected component. So by studying the X-ray spectra of the AGN, we can guess or get certain information about the whole shape of the torus that is reflecting back at us. However, in order to be able to do that, we need high energy X-rays. So if you see here, this vertical line that I'm showing is the 10 keV range, or the border between softer X-rays and harder X-rays. If we want to see anything above here, we need an instrument such as Nooster. So without Nooster data, it is very difficult to disentangle between all the degeneracies, between the multiple parameters that are affecting the shape of the reflected component. So we would expect that if the torus is patchy, as it turns, the amount of the shape of the transmitted power load, the line of sight component, will be affected by changes in our line of sight, since the torus is changing and we're always piercing through a different spot. However, the shape of the reflected component, we do not expect that it will change at short time scales, let's say a few decades. That is because at such large scales, it would need a much longer time to change in any significant way. So as we have multiple epochs, we expect to constrain the shape of this reflection component better and better because we expect the shape to not really change. Another clue that we have to the fact that the structure of the AGN torus is complex and that the material is not perfectly homogeneous can be done when comparing the properties of the line of sight through the average properties of the torus. These are some results from X-ray modeling of AGN in single epochs. And I'm plotting the line of sight column density, the amount of material in the line of sight, versus the average density of the torus as derived from the modeling of this reflection component. And this diagonal line is the one-to-one relation. So as you can see here, none of our AGN tends to fall on this one-to-one relation, meaning we expect that the material, or this may be a hint that the material is actually not homogeneous at all, right? We are piercing the torus through a direction that's not particularly representative of the average properties of the torus. And one could expect that if we have multi-epoch data in X-rays of this AGN, the points would move up and down, but would not move in this horizontal direction because the average properties of the torus would not change. So the motivation behind a study that can explore changes in DNH at different epochs is that it can help us further characterize the properties of the torus. For example, previous works have shown the capability of this method to determine certain properties of the obscurer, a work by Maiolino et al. So certain cometary tails in the clouds that are responsible for obscuration. For example, they monitored quite constantly a particular AGN, and they saw a sharp drop in emission corresponding to a high increase in an age, very sudden increase in an age in the line of sight, that then recovered quite slowly. meaning that the material, which in this case was assumed to be a broadline region cloud, would have a shape similar to a comet in the sense that it would have a much thinner tail as it moves quite quickly through the interstellar medium. A shock generates or forms in the direction of movement, but in the other end, the material is a lot thinner, right? Other things that can result interesting from this, however, is a result particularly found by Laha et al. In 2020 in a sample of 20 nearby Sniffer-2 galaxies that they showed, or they saw that by studying multi-epoch spectra, only 7 out of 20 were showing changes in the column density in the line of sight. So one could wonder, okay, if the torus is patchy, and we're all quite certain that this material is patchy, why don't we see variability in all of our AGN? Why are there so many of them in which we see 2 epochs, or three epochs, or 10 epochs, and in age is always the same? Is this actually against the idea of a patchy torus? How do we actually explain that? And this is a question that we cannot currently truly answer. So far, however, the majority of studies on age variability are focusing on single sources. So it is very hard to derive this sort of general properties or answer questions such as, okay, so how many AGN are actually non-variable in obscuring column density, and how many are actually variable, and is this percentage compatible with our understanding or current understanding of the torus of an AGN? For example, the most extensive study that has been used for calibration of current patchy torus models for the infrared and X-ray has a continuous monitoring of a variety of objects, and they only saw eclipsing events, or these changes of obscuration in our line of sight, in 8 of them, and only 12 individual eclipsing events. This is the most extensive study of this type so far. We're calibrating all of our models based on 12 single eclipsing events. So obviously this may be a little biased and calls perhaps for an increase of the sample. And here I'm showing the result of one particular eclipsing event shown in one of the studies. The first plot on the top is just a change in flux, or a ratio of flux between 2 different bands. As you can see, it keeps changing. And the other 3 panels are simply showing the age in the line of sight. So the data is the same, modeled in 3 different ways that may or may not explain better the shape and what's happening, what we think we're seeing, right? The first one is simply based on 2 different homogeneous spheres. Sorry, no, the first one is a single homogeneous sphere, second one, 2 homogeneous spheres, and this one would actually be shaped as a shell, so higher obscuration on the edges, much lower obscuration on the center as this plot passes through our line of sight. So with this type of data, you can try to play and try to fit the density profile of the clouds that are crossing your line of sight. So it has a lot of potential to tell us properties of the material in our line of sight. Here is the example that I am showing of how this sort of data can be used to calibrate current patchy models. This is showing the probability density also from the same work. The probability density to see an eclipsing event in X-rays as a function of the time scales that we're expecting, right? And as you can see, even if you can try to fit some sort of model to this, type 1 AGN, type 2 AGN. For type 2 AGN, we have only 4 individual events. So what we can do is frankly very limited at the moment. So based on this, the objective of my work right now is to try to use changes in the line of sight and age of AGN using different observations of the same AGN to try and constrain various parameters of the torus. And at the same time, try to correlate them to the shape of the torus that we are obtaining by studying the geometric properties from the reflection component. This is the idea, trying to do an interplay of what both components can actually tell us. As I said before, we don't expect the reflection component to change in shape in the timescales that we are considering, which is an advantage when one is trying to constrain them. In order to do that, however, we must select an ideal sample of AGN that allow us to study both components, both the transmitted power law and the reflection component. And this you can only do when you have a certain level of obscuration. If you have too much obscuration, as you're seeing that very change on the top, if you wait for this to be like much higher than 10 to the 24, you only see the reflection. And then you cannot really constrain what's happening in the changes of transmitted power law because you don't see the transmitted power. Similarly, if you're actually using AGN that's not barely obscured, you only see the transmitted power law, and the reflection component is like 2 orders of magnitude fainter. There's no way you can constrain any of the geometric properties of the torus by using the reflection component. So you need a sample of AGN that can allow you to do both. So in order to do that, we use the sample of that Shuri used of 100 local BAT detected comptons in AGN. The BAT detection simply ensures that the AGN are very bright, so much better for our study. And the compton thinness, so we are asking for an NH that has, an AGN that has an NH in the line of sight between 10 to the 23 and 10 to the 24, again, so that we can study both components. To determine the torus properties of the sample, what Shuri did was use one Nooster and one soft X-ray spectrum taken from the archive, so not simultaneous. And as you can see here, this is the Nooster spectrum in blue, higher energies, and then you have a softer spectrum taken with XMM. And as one can see, these two spectra don't really overlap. This is because they were taken at different epochs. So we can ensure that we are seeing some variability happening in this AGN at 2 different epochs. So Shuri saw that for his sample, 31 out of 100 AGN needed to include some form of variability in order to be able to explain and correctly fit the spectra. Of the 31, in some of them, he requires some variability in the NH of the line of sight, much as this one. As you can see, the 2 values of the NH determined for each epoch are not compatible with each other. But for some others, what he saw is that he required variability in intrinsic flux. However, when we have so many components in the AGN spectra in X-rays, sometimes this entangling between one type of variability and the other type of variability is non-trivial, particularly if you only have 2 observations. So I decided to consider all of these 31 AGN as potentially variable in an age in the line of sight. And it turns out that 18 out of them had more archival observations than the 2 Shuri had already analyzed. So this is my starting sample to try and build a bigger sample of NH that are potentially variable in the line of sight. In order to analyze these sources, I looked at all the observations simultaneously using self-consistent physical models of the torus, my torus, Boris, and Eurex clumping. And what I'm doing here, this is one of the examples, 3 different spectra, 3 different epochs. And there's a change you can see in the shape of the spectral shape, and particularly at softer energies, we see a change of curvature. This is particularly indicative of the presence of some difference in the amount of obscuration in our line of sight. But the changes that we see in the spectrum at higher energies tend to come from intrinsic flux variability instead. We need to take into account the 2 possible types of variability, fit them simultaneously. And at the same time, we are trying to constrain the shape of the reflection component, which is this dashed component under here, that's contributing significantly to the spectrum. And the fact that we need to explain 3 different total spectral shapes using the same reflection component actually allows us to constrain it much, much better than we would if we had one single epoch. This is an example of the work of one of our collaborators, Stefano Marchesi, who is fitting at 3 different epochs of another AGN, one taken February 2022, August 2021, January 2022. And these are confidence contours of 2 parameters, the inclination angle of the AGN and the average torus column density. Both of them we do not expect will change at in such a small timescales where the inclination angle shouldn't change at all. And as you can see, at the 3 distinct epochs, the confidence contours are not very constraining. But once we fit the 3 epochs together, we get much, much tighter constraints in the actual parameters of this AGN. So what we're trying to do is relate these very well constrained torus properties to the properties of the variability of the column density in the line of sight. And so far, we've analyzed a pilot project that's already published, and my current paper that's already been submitted contains 12 additional sources. We also have an ongoing monitoring campaigns and in-depth analysis of particularly challenging sources. And we've analyzed more than 100 individual observations. The results so far look somewhat like this. What we do is we plot the NH as a function of time, starting from the first observation that we have of that source, counting in days. And the data points, such as these ones, are the NH in the line of sight at a particular epoch, derived with the 3 different models. So a good conclusion from our work is that, well, the measurements seem reliable because every model that we use gives us very compatible measurements of the NH in the line of sight. We're very happy about that. And we're comparing also this variability to the average properties of the torus. The average NH of the torus, as derived from our models, is these dashed horizontal lines with the dashed area, meaning the error range of the derivation. So in such a case, the first source would be non-variable in NH because all of the data points are compatible with each other. And it's also compatible with the average NH of its own torus. This is a very non-variable scenario. The other one, however, is very variable because at different epochs, it just goes up and down. And interestingly, it is not at all compatible with the average NH of its own torus. What we've derived in our analysis is that we can ascertain that 5 of the 12 sources are variable. 5 of them, we cannot say that they're variable based on the data that we have. Of course, it could be that in between all of these 3,000 days, at some point, it went up in NH or down in NH, but we don't actually know. So we cannot claim that they're variable, and we call them non-variable. And for some sources, we actually cannot determine, for 2 of them, if the variability is coming from intrinsic flux variability or from obscuration in the line of sight. So we call them undetermined. Something that's very interesting, however, is that the majority of our sources look very much like the 2 here in the bottom. So even though we're seeing NH variability, the data goes all up and down, it never intersects the average column density of the torus, as one could perhaps expect. In fact, for 7 sources, our NH, our obscuration, is always much higher than the NH that's responsible for reflection. And for a couple of sources, we see the opposite scenario. And this is suggesting perhaps a physical disconnect between what is the reflector in our torus and what is the obscurer, what is the material responsible for obscuration. If we want to explain what we're seeing in these cases in which we're seeing intense reflection, it may be simply that we have a very strong reflector, for example, a ring of material, such as this one here, and that we are not intercepting. We're seeing through a cloud distribution, and we're not intercepting a very thick flat ring of material that's mostly responsible for the obscuration. This is something that has been proposed before, and it's been said that it could be even a warped accretion disk itself that is responsible for this. In the case of having a much thinner material responsible for obscuration, that is much harder to explain because you have something there that's obscuring you, you know that. Why is that not reflecting? It shouldn't really be happening. We know that we must not have this thin reflector or reflection ring closer to the AGN, but what is it then that is causing the reflection? And the answer may be that we have simply a multi-phase medium. And this has been proposed for usage in some infrared observations. It seems to explain infrared observations very well. And what could be is that we have a diffuse medium, which is the reflector that we're seeing, and it's a very optically thin medium. And the cloud distribution is acting mostly as the obscurer. So why are not the clouds reflecting? It could be that they are, but when we have a spectrum much as this, we cannot disentangle between the contribution of so many components. And we may be fitting the thin reflector, which is this blue line here, the obscured line of sight, which is the red line. But since we're not adding a third component, which would be the thick reflector, because we simply cannot disentangle between so many different things, our model prefers to give us this thin reflector that contributes very heavily in this range, instead of giving us a thick reflector whose contribution may be being absorbed into all the other components that we're using to actually explain the spectrum. We think this may be what we are saying. To give you some general results of the sample and some idea of how keen this may be used perhaps in the future, we're showing here the average properties of variable and non-variable sources. I have to say, though, disclaimer, none of these are statistically significant because I have 5 sources in each bit. And the middle one, the undetermined, only has 2 sources. So this is very high errors, but giving perhaps we're seeing some hints of some difference between the not variable and variable sources. For example, not variable sources seem to have much lower cloud dispersions, meaning the clouds seem to be distributed in a flatter way compared to variable sources, in which the clouds in the torus seem to be larger distributed. In the same way, if we're plotting the time average line of sight, so this is the average density of our line of sight of the obscurer, it seems that variable sources tend to be more obscured in average. And they also seem to have higher differences between this average obscuring density and the torus average NH, meaning the density of the reflector. Larger differences between the density of the obscurer and the density of the reflector. Ways in which we are expecting to be able to use this to constrain proper torus properties is plotting quantities such as this. I'm showing in here the difference in NH between two consecutive observations of the same AGN versus the difference in time at which these two observations were taken. And as we can see, we only see large differences in NH at large timescales. We're not seeing large differences in NH at very small timescales. This could be suggestive of the obscurer having large distances from our source. Because if everything was coming, for example, from broadline region clouds, one would expect to see also large differences in NH or the same type of differences in NH at all timescales. However, again, we are missing a lot of data. This is 12 sources. We don't have a lot of observations at shortened timescales. And since we're using archival observations, we cannot really choose our own timescales. What we need to do at this point to be able to properly use plots like this to calibrate models, like just randomly select directions in models and see if we're obtaining results that are fitting the data, what we need right now is many, many more observations. This is the conclusion of my talk, and I can leave you here with the summary and our future work. Thank you.
Thank you, Nuria. We have time for maybe 2 or 1 quick question, so we can go from the online attendees. So maybe we can from here, the in person, if you have any questions for Nuria. So maybe I can start. So Nuria, so you compare your sample of your sources, these 12 sources, with the previous measurements in 2014. So what's the difference of your samples and their sample?
Mm-hmm. So the measurements taken in 2014 were measurements, I believe, by RxTE. So it's mostly very, very bright sources that went monitored constantly through a relatively short time span. And there's a lot of Seyfert-1 galaxies that have very small individual, very few obscuration events, very sparse, and a very small sample of Seyfert-2s. So I would say the main difference is that we have much higher obscuration on average in the line of sight, and also that we have many more sources that we are looking at compared to what they were able to look at. So we're expecting to find something more representative and more numerous compared to what has been done before.
And also you are using NuSTAR observation.
I am using NuSTAR observation, so we expect our measurements to be more reliable because we're much better at disentangling variability so intrinsic flux variability, intrinsic luminosity variability of the AGN, and variability in NH in the line of sight. And we also have the capability to compare what we see to average torus properties that we're deriving from the study of this reflected component.
Thank you.
Thank you, Shuri.
Thank you for the talk, very interesting. I think the sampling for this not variable, determined variable, is the same in the sense of the.
Yeah, it's random. It's random.
It's random.
Yeah, because it's archival observations. So this depends on what other people wanted to observe and when. So we have absolutely no control about this, but there's no particular difference in sampling between the variable and non-variable sources.
No, I mean if there are variability, not variable object, but in different scale.
Oh yes, it could be.
No?
Yeah, absolutely, it could be. So the definition here as non-variable is more like we cannot claim they are variable.
Okay. Yeah.
That is actually, we're not sure if they're variable or not, exactly, we cannot tell. But we're still interested in plotting something like this to see if we saw any sort of difference in behavior. So my student is currently working on doubling up the sample and we are interested in seeing if this sort of behavior, so if this trend strengthens or gets completely destroyed when we double the amount of sources that we have.
Thank you.
Thank you.
Let's thank Nuria again. So our second speaker is the online speaker. So maybe when Amy is working on this, I can introduce the second speaker. So our second speaker is Dr. Sana Sois Papinauya, and I think he can correct me later. And he's a senior researcher at the Institute for Astronomy and Astrophysics, Space Applications, Remote Sensing of the National Observatory of Athens. Sorry. And he studies how particles are accelerated during solar energetic events, escape from the sun atmosphere and propagate through space to reach Earth and other planets. Additionally, he implements innovative algorithms to predict their radiation impact. He further investigates the effect of large-scale propagating magnetic structures in the interplanetary space on particles of galactic origin, leading to short-term decreases. Finally, he assesses the potential habitability of exoplanets through the quantification of the impact of the particle environment. He obtained his PhD from the Department of the Physics of NKUA in Athens, and I think.
Do you want to go ahead and share your screen?
So, Sana, yours. The floor is yours.
Hello. Okay. So thank you for the opportunity to present our work in your seminar. So I'm going to discuss the sun as a star analog, and specifically I'm going to focus on the implications of the empirical solar energetic particle scaling relations. So a little bit of background. What I give you here is the stochastic acceleration in a solar flare. We can see the magnetic field lines with the green arrows. We have our reconnection site, and then we can see particles here with the blue arrows. These particles go downwards, hit the dense chromosphere, and from there we get the nice flare emissions that we record. And at the same time, we can have particles that go the other way around. So these are the solar energetic particles that are being released to the interplanetary space. Now, on top of solar flares, we may see also coronal mass ejections, so CMEs. And this is basically an expel of plasma and magnetic flux, which is just ejected from the sun outwards into the solar wind and into the interplanetary space. And finally, when we have a coronal mass ejection that propagates outwards into the solar wind, it interacts with the solar wind, and it may create, if it's fast enough, it will create a shock, much like a bow shock. And that shock can accelerate particles and through diffusive shock acceleration, and these particles will be routed downwards to the observers following these magnetic field lines. So the take-home message from this cartoon is that everything is connected in the sense that our star, the sun, is a magnetic star. So we have magnetic energy that is being released, and it takes different forms. And usually one of the basic assumptions that we are making, whereas this is not the actual case, is that when you have a flare, you will see a CME, and you are going to see also particles. And how we see this in the measurements is like that. So basically, when you have a flare, you have all these nice signatures. You have your hard X-rays, for example, your soft X-rays. Then you see radio waves. You can also follow self-expansion of the CME, and you can see this high time. So you can see how this propagates into the outer corona. And then when you have your flare and your CME, you may also see particles, and particles that have a higher velocity, so a higher energy, will arrive first, whereas particles that have a lower velocity or lower energy will arrive later. And it all comes down to these simple schematics. So you have a star, the sun in our case, you have an eruptive flare and a CME, it drives a shock, and then you see particles. Now, one of the questions that has been around for many years was if we can infer the peak proton fluxes from the solar flare characteristics, so specifically from the soft X-rays. So what I give you here is a typical example. What you see here is the soft X-ray flux in watt per square meter, and the peak of the soft X-ray flux is this blue circle here. And on the top panel here, you can see particles at different energy ranges. So basically, the peak proton flux is denoted here for that specific channel with a red circle. So the question is if there is some kind of relation or correlation between these two peaks. And the answer is that yes, indeed, there is some kind of relation. So what I give you here in the logarithmic space is the peak proton flux versus the soft X-ray intensity. This is a cloud of points for a specific energy of interest. So this is the particles with an integral energy larger than 10 MeV. And there is some kind of linear relation. So it all comes down to this mathematical formula. And what you need to do is to define for your sample this alpha parameter here, this exponent. And there's a lot of literature on this for many decades now. Now, Takahashi and co-workers in 2016 were the first that considered the upper limit. So what I give you here is a similar plot as before. So on the y-axis, we have the peak proton flux, and on the x-axis, we have the soft X-ray flux. And this is the cloud of points that Takahashi and co-workers had. This is their typical scaling relation, so something like that. And then they introduced this dust black line here, which goes through the uppermost point of their distribution. And they introduced that based on theoretical consideration. So they assumed that the mass of the CME is the sum of the mass in the active region, that the kinetic energy of the CME is proportional to the flare energy, and that the flare energy is a fraction of the active region energy. They also assumed, for example, that the total proton energy is proportional to the flare energy. And from that, they derived that the peak proton flux, the upper limit peak proton flux, should be proportional to the soft X-ray flux with an exponent of 5/6. So what we wanted to do in our work was to investigate such upper limits. So this is a similar plot from our work. So you see here again in the y-axis the peak proton flux, and in the x-axis the soft X-ray intensity. We compiled the list of 65 well-connected SCP events. We wanted them to span from larger than 10 MeV to larger than 100 MeV. Here in this plot, I give you the larger than 10 MeV. So these are actual measurements. All of these SCP events were associated with flares and CMEs. And I should mention here that we use the corrected soft X-ray flux. This is something that it is ongoing by Hugh Hudson and Ed Cliver. And we also used as a fit here the reduced major axis, so an RMA fit. And we applied this upper limit that was proposed by Takahashi, a scaling with the soft X-ray flux with an exponent of 5/6, and we got it through the uppermost point of our distribution. And for comparison reason, I also plot here the Takahashi et al. Upper limit here with a dust red line. Now, the next step in our investigation was to try and see if we could go further from this energy, from the 10 MeV, to go and see in larger energies and higher energies if something like that stands. And what I give you here are similar plots for the larger than 30 MeV, larger than 60 MeV, and larger than 100 MeV. And as you can see, it seems that the theoretical considerations that Takahashi employed, so this upper limit with the soft X-rays with an exponent of 5/6, seems to be applicable to all other integral energies. Now, there is an intermediate step in our calculations. It has been known for decades, but there is a very nice paper out by Steve Keller in 2018. So basically, there is a relation, a linear relation of the peak proton flux of an SCP event versus the fluence. So the fluence is the integration of the over time of the SCP density. And we did that for our sample for 4 different energies. So basically what this plot means is that if you have your peak proton flux, if you can identify that, then you can translate that to fluence quite easily. And then we utilized all these steps, and what we wanted to achieve is to try to get the fluence, to get an upper limit of the fluence based on soft X-ray measurements. And what we did is that we turned it to our sample, the 65 events. What I give you here in the y-axis is the omnidirectional fluence, which we calculated for each event at that specific energy versus the soft X-ray intensity. And here is the typical RMA fit for the whole population. And this is just the RMA fit scaled up to go through the uppermost point of our distribution. So what we actually did is that for all of these 65 events, we knew the associated solar flare. So we used the Takahashi scaling in order to infer the worst case scenario peak proton flux that such a flare could give us. Then we translated this worst case peak proton flux to fluence, and then we derived a scaling of an upper limit scaling of the fluence with respect to the soft X-rays with an exponent of 5 over 6. And this is what I also give you here. So we did that for all 4 energies, so larger than 10, 30, 60, and 100 MeV, and it seems to stand at all cases. Now, the last part in our calculation was to get the fluence integral spectra based only on soft X-rays. So if you know the flare, the associated flare of your SCP event, is it possible to derive the fluence integral spectra? And in order to do that, just as a recap of the different steps, we have the soft X-ray, so we know the flare that was associated to that SCP event. We calculate the worst peak proton flux for that particular flare. We translate that to fluence, and then we derive the upper limit fluence for that particular flare. So we did that for 4 different energies, and in the end, we decided to fit these outputs with a simple power law representation. And this is how it looks in the data. Now, we wanted to validate this concept. So what we did is that we turned to case studies. So the first case study that we examined was the ground level enhancement 05 that stands for the largest SCP event that has been recorded on the face of the Earth. So GLEs are just large SCPs that are recorded by neutron monitors at Earth. And what you can see here is that this particular GLE has a 5,000% increase above background. So that's the largest GLE up until this day that we have recorded. And it occurred on the 23rd of February, 1959. Now, luckily for us, Ed, so Cliver and co-workers identified a soft X-ray flare. So what should be the magnitude of the flare that could lead to such a large SCP event? And they deduced this X20 plus minus 10, which with the new recalibration shifts to X28 plus minus 14. So the worst case soft X-ray flux, so the worst case, the strongest flare that could give us this SCP event would be an X42. So we use this in our pipeline, and from this X42 solar flare, we did use this orange line, which stands for the upper limit fluence spectra ranging from 0 to 500 MeV. So once we got this, we wanted to validate basically if this is actually an upper limit. And what we did was that we turned to the detailed reconstructions, because this was a GLE and this has been measured. So we have measurements by neutron monitors for that particular case. So there is this very nice reconstruction out for GLE05 by Ilya Ozovskin, Koldovsky et al. These are the guys from the University of Oulu in Finland. And you can see that this is the reconstructed spectra. This is the fluence, the integral fluence, and this is the rigidity, so basically the energy. So if you know the energy of interest, then you can come here and you can derive your fluence, what would be the integral fluence. And these are the blue points that I give you here for comparison with the upper limit fluence spectra that we derived. And there seems to be a relatively good agreement. And in all cases, the important thing here is that this should serve as an upper limit. So this should be beyond what was actually measured. And this seems to be the case. Now, we also investigate another famous study, that's the AD774-775 SEP event. In this case, we have radionuclides, so measurements of proxies. This is beryllium-10, this is carbon-14, this is chlorine-36. We see this large enhancement here, and there has been a wealth of papers out since 2015 that show that this enhancement here is of solar origin. And unlikely for us, in this case, we only have this proxy data. So what actually happens in this case is that the community takes the spectra from GLE5, it shifts it upwards in order to meet the actual fluence that is calculated by this proxy data. And then with the same logic for a specific energy, you can use this shifted spectra and derive the fluence. So again, in this case, Ed and co-workers identified the soft X-ray flux, so the flare, that could give ground to this large SEP event that would be an X285 plus minus 140, and that shifts with a new recalibration to an X400 plus minus 200. So that means an upper limit of X600. Now, in this case, when we utilize that in our calculations, so for an X600 flare, we derived this spectra here, scaled with the soft X-ray with an exponent of 5/6. And with the blue points here, I give you the shifted upwards spectra, the shifted upwards fluence from the spectra of Zoskin et al. With a factor of multiplied by a factor of 70. Plus minus 30, so this actually gives us the error bars. And what you can see here is that this upper limit orange line seems to be in reasonable agreement with the fluence that we independently got from the estimations of the proxy data. And it also possibly points to the fact that this may be the largest SEP event that has been released by our sun. Now, just to show you that we also did a similar work, but in this case, we utilized the CME speed. So we started off with the peak proton flux versus the CME speed. Again, this is the cloud of points. And now in this case, we have an upper limit scaling with, again, from theoretical considerations that scales with the velocity of the CME with an exponent of 5. And when we did the same pipeline, we were able to get the integral, the fluence integral spectra. And this is what I give you here. On the top panel, this is the GLE05. So in this case, the upper limit spectra is this dust blue line. And here are with the blue circles, you can see the measurements by neutron monitor. So the fluence reconstructed by neutron monitor measurements. And down here, you can see the results for the AD774-775 event. Again, this dust blue line is the upper limit fluence spectra that we derived. And with the blue, you can see the points that we got from the estimations of the proxy data. So this is in better agreement. And actually, the shape is better because it becomes harder. Now, there are also some implications concerning the upper limit of the CME speed. So what I give you here is the fluence versus the CME speed. Each panel, it's actually the same, but it corresponds to one specific event. There is a new paper out by the Koldovsky et al. Where they actually reconstructed the fluence based on the proxy data for a number of events, like similar, let's say, to the AD774-775 event. And what you can see here is that if we use this upper limit scaling, and we take for granted the fluence that has been calculated independently by Koldovsky et al., then we come here and we get a range of the CME speeds that could give ground to this 10 to the 11 fluence. And that CME speed should fall between 3,000 and 4,000 kilometers per second. And this is more or less the same if we also see the other three events for which we have these reconstructed fluence. But if we use this simple RMA fit, which represents the whole sample, then the CME speed that would be required in order to get this particle fluence would be between 7 and 9,000 kilometers per second. Now, what all of these have to do with the stellar energetic particles? Well, there is a milestone paper out in 2017 by Youngblood et al. So what they did is that they had these UV measurements. They mapped the UV measurements to soft X-rays using rescaling. And then what they did was that they managed to extract scaling relations using this transformation, let's say, of the UV to soft X-rays and get the peak proton flux. So if, and the fluence, so this is the integrated proton flux here, is the fluence for the energies larger than 10 and larger than 30 MeV. So basically, if you have measurements and you know what is your flare, then you can come into these scaling relations and derive an estimation of your peak proton flux or fluence. And in our case, what we have done actually falls under this under this paper in a sense, because now if you know the flare or the CME, then you can directly derive the fluence, the integral fluence, up to 500 MeV. And the question is if this sun as a star analog works. So this is just a comparison of the flare frequency. So how many flares we have. This is a very famous picture. How many flares we have. And this is a comparison of the actual sun-like flares and the solar flares. And we can see that there is a pretty, let's say, consistent power law with a slope of 1.8. That seems to go across solar flares, non-solar flares, and sun type or sun-like stars. Now, finally, there is a nice paper out that actually did it the other way around. So they actually modeled what would be, I mean, they have this nice model with the three components. So you have an MHD component that tells you what your solar wind is and what your CME is there. You have a nice cell where you accelerate your particles and then you transport your particles downwards the IMF lines. And from there, for different speeds ranging from 1,500 to 3,000 kilometers per second, they got these fluence numbers for the 430 MeV. So this is basically comparable to what we have done there, and we wanted to make this comparison. So what you see here with the red bar is actually the fluence that they derived through their modeling. And as you can see, there is a good agreement between the upper limit scaling law. So this continues to be an upper limit in this case, but these are within reasonable agreement with all the assumptions that we have of both cases. I should also mention that there is some kind of scaling relation that scales the CME speed and the energy to the flare class here. There seems to be some overestimation here with the soft X-ray class. And I should also mention that the scaling laws that we're proposing here clearly overestimate the fluence at higher energies because we don't apply this DSA theory, so we don't have this expected rollover of the spectrum. And now for the conclusions, just some thoughts. For the sun, we have high resolution multi-wavelength measurements. We have in situ measurements. So we have specifics. So that means that we can constrain our models and extract valuable relations. For the stellar case, at least to my knowledge, we have massive statistical information of solar flares. We have thousands of solar flares, but we don't have detailed information on the stellar winds, on the stellar and the planetary environment. So it is difficult to constrain models and to extract physically valuable relations. However, extrapolations within assumptions and problems are a viable first step. This provides this estimation of the worst case scenario for the particle environment, and it's a quick way of doing that. And it seems that scaling laws and modeling efforts can be beneficial to each other. And with that, I would like to leave you and thank you for your attention.
Thank you very much. Do we have any question online or in person? Oh, so Scott, please unmute yourself.
Oh yeah, so I was very nice talk. I was trying to understand if and how the model maps the mass loss in the CME. I see the energy of the peak proton flux and the energy in the CME, but how's the mass working? Does the mass work into that?
We didn't consider the mass ourselves. The model is not our model here. This is the Hu et al. Model, so it's the IPATH from the Huntsville. I am not really sure how they utilize the CME mass.
And when you do the fitting, you're just looking at the energies, not the masses, right?
Yes, because I know that for this specific velocity of the CME, they infer this with their model. They know this actual fluence, and this is directly comparable to what we're doing because here we have the energy that's an integrated integral energy, and this is the 430 MeV right there.
Okay, thank you.
Okay, you're welcome.
If no other further question, let's thank both speakers again. And see you next week. Thank you.
Thank you. Bye.